Thanks for the introduction. So hi everyone, I'm David, and today I'll be talking to you about privately evaluating decision trees in random forests. This is joint work with Tony Fone at Stanford and Michael Nayrick and Kristen Lalter at MSR Redmond. So in the last few years, one of the trends that we've been seeing is this notion of machine learning as a service, right? It's about taking big data and machine learning algorithms and putting them in the cloud so that many people have access to them. I'm going to give you an example from the medical domain. So consider suppose we have a physician who's trying to diagnose a patient with a disease and trying to figure out what the optimal treatment plan is. How can the physician take advantage of some of the big data that's available to help with this procedure? Well, what the physician can do nowadays is she can now go and collect a bunch of measurements about the patient, look at the list of symptoms, and submit those features to the cloud, and hopefully the cloud will have some new information or some something that will assist with the treatment and potentially propose a recommended treatment plan. So this is all good, but when we think about this from the privacy perspective, suddenly there's a lot more new challenges. For instance, if an adversary subverts the cloud, then it basically learns all of the patient information. So if we have a medical example where physicians are sending patient data to the cloud and the cloud is no longer trusted or the cloud has been subverted, then suddenly we are compromising the patient's privacy, which is very significant in many scenarios. Conversely, suppose instead that the adversary is on the client side. The adversary is going to pretend to be a physician or a doctor and going to send malicious data to the cloud in order to try and learn something about the model that's being used by the cloud. Now, when we talk about medical information, when we train these models, they're usually trained on patient data themselves. And by making adversarial queries to the model and potentially extracting information from it, they can potentially compromise the data that was used to train the model itself. And so a malicious client might recover more information than they should about that underlying data, and in turn, again, compromise the privacy of individuals whose data went into the construction of the model. So in this work, we're going to look at the problem of how do we privately evaluate a model in the cloud. And for the purposes of this talk, we're going to restrict our attention to one particular class of models, namely decision trees, which are nonlinear models that are very commonly used for regression or classification. And these models are useful because they're interpretable. Oftentimes, they are very simple. So here, I'm going to give you a brief overview of what a decision tree classifier is. So the input to these decision trees is going to be a feature vector. So in a medical diagnostics example, this feature vector might be the patient's weight, height, other metrics, and potential symptoms that they are potentially experiencing. To evaluate a decision tree, we begin at the root node shown here, and we basically apply a bunch of tests. And these tests essentially are comparisons in our setting. So we're going to look at an entry in a feature vector. We're going to compare against some fixed threshold. Depending on whether it's greater than or less than, we're going to either move left or right. And this proceeds until we hit a leaf node. And each leaf node in the tree, highlighted in blue here, is associated with some value. That is the value of the decision tree on the user's input. So when we talk about the problem of fully private decision tree evaluation, we can abstractly formulate it as a two-party computation problem. And I'm going to only give you the abstract idea here. All of this can be formalized in the real ideal world setting, and I will refer you to the paper for the full details on that. But abstractly speaking, we have a client and a server. The client on the left here holds a feature vector x. The server here holds a decision tree t. And basically, they're going to engage in some kind of two-party computation protocol, such that at the end of the two-party computation, the client only learns the evaluation of the decision tree on the chosen input and maybe some additional metadata or metaparameters related to the decision tree itself, but nothing more than that. And privacy for the client says that the server at the end of this protocol execution does not learn anything about the input that was supplied by the client. So for this talk, we're going to focus on a problem of model evaluation. We're going to assume that the server, i.e. a cloud, an organization, a company, they've already trained some model, and now they're sort of outsourcing this model evaluation to the cloud in the sense of providing it as a useful service to interested clients. So before I go into the construction of our particular protocol, I'm going to elaborate on a few approaches that have been proposed for solving this. So on the one hand, we have generic methods based on somewhat homomorphic encryption. So additive homomorphic encryption and leveled fully homomorphic encryption. This was proposed by Bost et al. In NDSS of last year, where they showed how they can use some of these primitives to build a wide variety of machine learning classifiers. Unfortunately, these protocols tend to rely on fairly hefty cryptographic primitives, and as a result, they are both computationally and bandwidth heavy, but they do give a protocol for evaluating arbitrary decision trees. On the other side of the spectrum, we have Yau's-Garble circuits, which also gives a solution for evaluating these decision trees in a privacy-preserving manner. These Yau circuits, due to the optimizations in two-party computation from the last few years, these are extremely efficient, but again, the communication seems to be the bottleneck in a lot of these generic methods. So in our work, we're going to look at some trade-offs on the communication bandwidth spectrum. And in exchange for lower communication costs, we're going to have the clients and servers do a little bit more work compared to Yau's-Garble circuits, but significantly less work compared to using homomorphic encryption-based techniques. Right, so the fundamental building block, as you might imagine, since we're evaluating decision trees, is some way of doing comparisons. We need a protocol that allows us to compare the components of the client's feature vector with fixed thresholds on the server's model. I'm not going to get into the details of this, since this is more or less just prior work. There are many examples of comparison protocols, and the one that we use in our case is one proposed by Darmstadt et al. In 2007, and also used by Bost in 2015. So abstractly, the comparison protocol provides the following guarantees. Both is a two-party computation where both the client and server have a secret input, an integer x and y, and basically they engage in a comparison protocol such that at the end of the protocol execution, the client learns whether x was less than y or not. It learns the comparison bit, the server learns nothing. This is a special case of Yau's millionaires problem, if you're familiar with that. So how do we use this comparison primitive to build a private decision tree evaluation protocol? Well, here I'm going to give a strawman candidate. This doesn't actually work, but I think it highlights most of the intuition that goes into the construction of this protocol. So suppose, for sake of argument, that the client for somehow knew the decision variables at each node in the network. So in particular, the client knows that at the first node, the value of the decision variable is 0, and therefore it should go left, and correspondingly at the other decision nodes. What this allows the client to be able to do is the client can now compute the index of the leaf node that corresponds to its evaluation. So if the client knew the value of each decision variable, the client can just compute the index of the leaf node by itself by just evaluating or following the tree traversal procedure. So now what happens? Well, the client now knows the index of the leaf node that contains its evaluation output. The problem basically reduces to an oblivious transfer protocol, where we treat the leaves of the decision tree as a database, and the client knows the index. It can just simply do OT to learn the decision tree value at the indicated output. So just to recap, an oblivious transfer protocol is also a two-round protocol. It's a two-party computation where the server here holds a database of values. So this is a 1 out of n protocol. So the server holds a database containing values x1 up to xn, and the client holds a single index I. At the end of the protocol execution for an OT protocol, the client learns only xi. So the entry and the ith component, or the ith record of the server's database, and nothing more about the other entries in the server's database. The server learns nothing. In particular, it does not learn which input the client requested. Okay, so just to come back to the private decision tree evaluation, how do we use OT to solve the problem? Well, as I described earlier, if we assume that the client knew which leaf node it landed at, basically, it can just do an OT where it requests that particular value, and the server runs the OT protocol with the values of all of the leaf nodes, and this in turn reveals to the client the requested outcome. Okay, but as I described earlier, there's a very significant problem with this protocol in the sense that it requires the client to both learn or at least know the structure of the tree in order to carry out this procedure. The client, if they do not know the structure of the tree, they cannot compute the index of the leaf node to request an EOT protocol. So most of the rest of the talk will be on how do we actually address this. And it turns out that for semi-honest secure evaluation, it's actually quite simple. It contains 2 steps. So the first step is, well, how do we hide the structure of the tree? One simple way of doing that is we can insert a bunch of dummy nodes to pad the tree in order to obtain a complete binary decision tree. So of course, this does incur an exponential cost potentially in the worst case. But what it means is that we can now reveal the structure of the tree. It's always a very simple tree. we just tell the client the depths of the tree, and now the client can compute the structure. Of course, this by itself is not sufficient, because if the client knows the decision variable at every internal node in a decision tree, it learns the path that her feature vector took during the decision tree evaluation process. This path can again reveal information about the structure of the tree, which reveals information about the model. So to protect against this type of attack, we introduce a randomization step where we basically randomly swap the left and right subtrees of each of the decision nodes in the graph. So as an example, here we're going to swap the root node. So instead of comparing against a fixed threshold and going left if it's less than and going right if it's greater than, we're going to, with probability 1/2, flip the left and right subtrees, and correspondingly, also instead of using a normal decision variable, use the negated decision variable. So in particular, after we apply the randomization process, we can show that on any given input vector, the path through the decision tree is actually uniformly random over all possible paths. And so this is a uniformly random string. It does not reveal any information about the structure of the tree to the client that evaluates it. So to summarize, our private decision tree evaluation protocol consists of the following steps. So first, the server is going to start by padding and permuting a decision tree. Then the server and the client are going to engage in this comparison protocol to learn the values of all of the decision nodes. The client is going to then compute the index of the leaf node in a permuted tree, and it's going to engage in an oblivious transfer protocol to obtain the value of the decision tree on her chosen input. In a paper, we show that this protocol is secure against semi-honest adversaries. So in a full paper, we also describe several extensions, which in the interest of time, I will not be able to get into. I'll just describe them for you here and refer you to the paper for further details. One extension that we show is that instead of evaluating a single decision tree, we can actually evaluate a random forest, which is basically evaluating an ensemble of decision trees and then aggregating the results by taking a mean or like a majority vote. In particular, we can show that with a simple extension of our protocol, we can evaluate the random forest without revealing individual classifications of the trees that comprise the forest. Another thing that we show in a full paper is that we can actually get a security against malicious adversaries without too much extra effort. And this is especially important because when we talk about deploying these protocols in the real world, we're really interested in malicious settings, and semi-honest settings are often not sufficient. Okay, so to conclude the talk, I'm going to give a few benchmarks of this protocol and compare it to some of the existing literature. So we implemented the private decision tree and random forest protocol, and then we took a series of benchmarks with a client running on a laptop and a server simulating an actual deployment scenario on an Amazon EC2 instance. So here's a toy example that has been considered for previous work on private decision tree evaluation. So this is a decision tree trained on electrocardiogram data used for predicting heart disease. This is a very simple scenario. The data dimension contains only 6 features, and the decision tree that's trained on this contains its depth 4 and contains only 6 comparisons. But I think it's sort of illustrative to see how our protocol compares to some of the existing protocols. So here at the top, we have the Barney et al. Protocol from 2009. This is a protocol based on Yells-Garble circuits, and the BOAST protocol based on somewhat homomorphic encryption from last year. And basically, the takeaway here is that our protocols are roughly 10 times faster than the previous protocols because we're really combining efficient protocols for comparisons with this oblivious evaluation procedure. So that was a toy example. That's probably not indicative of many real-world applications. So another second experiment that we looked at was looking at the scalability of our decision tree evaluation protocol. And here, we're looking at evaluating complete decision trees. While these are not likely to arise in practice, this sort of gives a worst-case bound on the runtime and performance of our algorithms. So here we show for evaluating decision trees ranging from up to 4 nodes to something about 10,000 nodes, the protocol scales reasonably well. So for a decision tree containing almost 10,000 nodes, the complete protocol execution finishes in a couple minutes, so basically in about 5 minutes or so. And the bandwidth is only a couple of tens of megabytes. So not ideal, but potentially very practical for a lot of these cases where high throughput is not essential. And certainly, if we're looking at smaller decision trees, our protocol performs quite reasonably. So to conclude, in this talk, I have introduced some simple protocols for decision tree evaluation. I described how the protocol works in a semi-honest setting, but we can easily extend it to the malicious setting. And furthermore, we hope that I've demonstrated that semi-honest and malicious secure decision tree protocols, by building custom protocols, we provide new computation and communication trade-offs. And with that, I'll open the floor to questions. Thank you.